All right, this is Thursday, January 7th, 2021, Physics CP. I'm beginning the process of teaching students how to do a Coulomb's law net force calculation when I have more than just two electric charges. So we've made up a random problem, and the random problem says I have three charges all in a row. And this school year, we're always going to do it just one dimensional. They're always going to be in a row. The first charge, Q1, is positive 2 millicoulombs. 5 meters to the right of it, charge Q2 is positive 6 millicoulombs. 7 more meters to the right from charge Q2, charge Q3 is negative 3 millicoulombs. And even though I wrote these to 1 sig fig, let's calculate it to 3 sig figs for all the values. So 5.00 meters, 6.00 millicoulombs, and so forth. There's really one more question that I should toss out there. And the question is, for which one of these three charges should I work on to calculate the net force acting on that charge? I could choose Q1 or Q2 or Q3. I was going to call on a student, but I think for educational purposes, I am going to declare I'm going to choose Q1. The answers will be different for each of the three charges. And so my question is, what is the net force on charge Q1? That's what we're going to try to solve in our remaining few minutes. To do this kind of a problem, you have to first recognize that Coulomb's law says the force of electrical attraction or repulsion between any two electric charges is equal to the product of lowercase letter k, the Boltzmann's constant, times charge Q1 times charge Q2 divided by r squared, the distance squared between each of those two charges. Now, this formula only has two charges in it, but this problem has three charges in it. And so you might foolishly think, oh, what if I just multiply this by Q3 and then multiply it by, I don't know, something down there? That would be the wrong way to do this. Coulomb's law can only be used for one pair of charges at a time. So as you look at this problem that has three charges in it, first identify which one is the one that we're working on, and that's going to be, in this example, Q1, the one on the left. The process is you shut off all the other charges, pretend they're not there, and then one by one turn on those charges. So first, I'm going to turn on charge Q2 and plug Q1 and Q2 into Coulomb's law, calculating the force of, in this case, repulsion between these two like charges. That will be the force pushing Q1 to the left away from Q2. After I come up with that number, I'm going to shut off Q2 and pretend it's not there and turn on the next charge, in this case, Q3. Now I have to be careful not to just foolishly say, oh, the distance from Q1 to Q3 is 7 meters, because it's 7 meters beyond Q2. Q2 is 5 meters from Q1. So my value of R is not going to be 5 meters. It's not going to be 7 meters. It's going to be 12 meters. and I ignore charge Q2, and I calculate Coulomb's law, Q1 and Q3. Now, in this case, they are opposite charges. So the force is going to be pulling Q1 to the right when I do that calculation. I'm going to end up with an arrow pushing to the left from Q2 and an arrow pulling to the right from Q3. I add those two arrows together, meaning they're vector sums, and that will finally answer the question, what is the net force on Q1? So there is the overview of the entire process. I will do this at ludicrous speed so that the recording shows the answer worked out before the period ends 7 minutes from now. All right, step one, or yeah, we'll call it step one. Calculate F12. Okay, calculate F12. I was going to say something else, but I scribbled it out. That would be F12 is Coulomb's constant times charge Q1 times charge Q2 divided by R squared. In this case, Coulomb's constant, I'm just going to write lowercase k, times 2 millicoulombs. So that's 2 times 10 to the negative third power coulombs times 6 millicoulombs. So that's times 6 times 10 to the negative third coulombs divided by the distance from R1, Q1 to Q2, which is 5 meters, squared. I don't remember if I said this before I started the recording, but we're going to presume that all of these values are known to 3 sig figs. On my calculator, then, I would type in alpha k, because I already stored it in memory, times 2 times 10 to the negative third power times 6 times 10 to the negative third power divided by 5 squared, enter. The calculator displays 4,315.2. So F12 equals positive 4, 3, and if I want to do this to just 3 sig figs, I'll round it off later. I'll do it to 4 sig figs. 4,315 newtons. Now this plus sign is a reminder that they repel, and so this is pushing Q1 to the left. That's what the plus sign means in this problem. Q2 is pushing Q1 to the left with over 4,000 newtons of force. Now I shut off Q2 and I turn on Q3. So calculate F13, meaning the force of electrical attraction between charge Q1 and charge Q3. That is lowercase letter k, Boltzmann's constant, times Q1 times Q3 divided by the distance from 1 to 3 squared. In this case, lowercase letter k, times 2 millicoulombs, 2 times 10 to the negative third power coulombs. The charge on Q3 is negative 3 millicoulombs. So times negative 3 times 10 to the negative 3 coulombs divided by the distance from Q1 to Q3 is 5 meters plus 7 meters is 12 meters. And I'm going to square that distance. Putting this into my calculator, I type alpha k 2 times 10 to the negative 3 times negative 3 times 10 to the negative 3 divided by 12 squared, enter. And the calculator displays negative 374.5832. So I'm going to say is equal to negative 375 newtons. Here, the minus sign means attracts. That means pulls Q1 to the right. Okay, so now, next step, I combine these forces. I've got 4,315 newtons pushing it to the left. I have 375 newtons pulling it to the right. So I will subtract 4315 minus 375, and the combined force, the net force, is 3,940 newtons, by the way, 3 sig figs, to the left. Now, in a normal number line, the positive x-axis is to the right, and the negative x-axis is to the left. So if you put it onto that coordinate system, then yes, you could say the net force is negative 3,940 newtons, meaning you understand it's going to the left. I did it with less than half a minute until the end of the period.